Okay, for my final project, I've chosen to talk about process scheduling. And in order to talk about process scheduling, I'm going to use a comparative approach. What we will discuss. First, we'll review some basic concepts, and then we'll look at some key alternative scheduling policies like RMS, EDF, and PTS. And then we'll talk about how to compare these. Using schedulability, CPU utilization, and system overheads. And then we'll go through a simple example, and we'll talk about that example comparing RMS and EDF, and then comparing using PTS. And then we'll talk about choosing a threshold and conclusions. And by the way, I assume you know RMS is rate monotonic, EDF is early deadline first, and PTS is preemption threshold scheduling. Okay, a review of some basic concepts. So we have something called the scheduler, and it uses an algorithm to make decisions about which job should run at which time. So it says here, using some algorithm, process scheduling is a decision process, method, or policy used to determine which task should be executed in any given point in time. So anytime something comes into the queue, the policy determines what happens next. Okay, there are two types of schedulers, preemptive scheduling and non-preemptive, and we'll talk about those shortly, and two types of scheduling algorithms, deterministic algorithms and dynamic algorithms. Okay, preemptive. Basically, as you can see from the example below, task 1 comes in because it has the highest priority, but then another task 2, say, comes in and it has a higher priority, so it preempts task 1, and then ultimately another task comes in this case task 3, preempts task 2. So task 3 finishes, then task 2 can finish, and then task 1. Now, in non-preemptive scheduling, a running task cannot be involuntarily stopped by the scheduler. The scheduler can only start a task and then must wait for the task to finish or to voluntarily return control back to the scheduler. So as we can see here, task 1 starts and finishes, task 2 starts and finishes, and then task 3. Okay, let's talk about deterministic versus dynamic scheduling policies. The priority assigned to each process is always according to some policy. A deterministic or static scheduling policy makes decisions offline, and those decisions remain fixed at runtime, which makes results ultimately easier to predict. A dynamic scheduling policy makes most of the scheduling decisions at runtime, so results are harder to predict. Of course, things like what the deadline must be and things like that, those decisions are made ahead of time, but which job actually runs at any given point in time is decided dynamically. Okay, some key alternative scheduling policies. Rate monotonic scheduling, RMS, is a deterministic preemptive scheduling algorithm which allows tasks with shorter cycle durations, i.e. periods, to interrupt running tasks with longer cycles. Earliest deadline first, EDF, is a dynamic, non-preemptive scheduling algorithm which schedules the next task with the closest scheduling deadline. And hopefully the example will help make that clearer. Now here's a newer one called preemption threshold scheduling, PTS. It's a hybrid method of dynamic scheduling which uses scheduling deadlines to determine the next task, but which also allows for preemption. By raising the priority of a process once it starts, you can limit the number of interruptions, right? This elevated priority for a process is called its preemption threshold. While obviously more complex than either RMS or EDF, PTS has been shown to offer advantages over both fully preemptive deterministic methods and fully non-preemptive dynamic scheduling methods. We will see this shortly. Okay, how to compare. How do we compare these alternative scheduling algorithms? Well, one key way of comparing is schedulability. Schedulability always refers to the worst case response times. Okay, and both pure non-preemptive schedulers like EDF and partial non-preemptive schedulers like PTS show improvements in the ability to meet deadlines over approaches like RMS. They also avoid pitfalls like thread starvation, where a task is never allowed to complete. Right? As we saw earlier, I mean, you could have a hierarchy of tasks all running where one task never finishes because it keeps on getting preempted by higher priority tasks. CPU utilization. Okay, if you add up all the individual runtimes and divide by their period, a utilization factor can be calculated. For RMS, a utilization factor greater than 69.3% has been shown to result in pure schedulability. However, EDF and PTS, with their focus on non-preemption, better CPU utilization schedulability results, but not necessarily for urgent tasks. That's a key point. Okay, another way to compare system overheads. Non-preemptive schedulers need significantly less threads in the same space, right? Each task that runs is a thread. And if you have too many threads running, this can cause problems. So non-preemptive schedulers need significantly less threads in the same space to oversee tasks when compared to preemptive schedulers, thereby reducing total memory costs. Okay, let's go through a simple example. Here we have 3 tasks. Task 1, runtime 50, period is 100. Task 2, 30, period is 90. And task 3, its runtime is 10, its period is 70. And let's assume a deadline double the runtime. So we've got 100, 60, and 20. Okay, so under RMS, task 3 starts first, then task 2, and then task 1 comes in the queue and starts. But it gets preempted by task 3. And it has to wait. And then it starts running again. And then task 2 comes in the queue and preempts it again. And ultimately task 1 is late. Okay, using the same 3 tasks, same scenario, EDF comes in. Now its scheduling is it's non-preemptive, which means, you know, one task has to start and finish, so there's no preemption, which is good. But tasks can still be late, right? Because we see here task 3, which has a period of 70, ultimately is late, and I'll show this shortly why this is so. Now PTS, in this example, although there's a wait still for task 2 and a preemption on task 1 for task 3, still all the deadlines are met, which is good. Nothing's late, right? Because we see here RMS, it's late here. PTS, there's no lateness, even though preemption still occurs. Okay, comparing RMS and EDF, we can see here worst case response times with RMS preemptive. We have a worst case response time of 130. So again, we're late. It's not good. And under EDF, task 3, we have a worst case response time of 100, which has passed a deadline of 90. So basically, the period in RMS, the period is the deadline. And we see 130 is greater than 100. And also over here, we see 100 is greater than 90. So that's where the lateness factor comes in. So using RMS, shortest period wins, right? The shortest, the task with the shortest period always runs first and continues to run. It can interrupt other tasks. Using EDF, the shortest task next, right? The shortest next deadline wins. So the task with the shortest next deadline wins. That's hard to say, but I think you get the idea. But what about PTS? Okay, now using PTS in the example that we just went through, if we chose a threshold priority of 2, a task with a higher priority, in this case task 3, can still preempt. But not all tasks with higher priorities can preempt, right? Task 2 has to wait. It can't preempt task 1. And in this case, worst case response times, all deadlines are met. Another way of saying this is all deadlines are guaranteed. Okay, so that's a very good result. But how to choose a threshold? Choosing a threshold. Each task has a preemption threshold equals to its priority, then our model degrades to preemptive scheduling. But if each task has a threshold equal to the highest priority in the system, then our model again degrades to non-preemptive scheduling. Therefore, some analysis is required, but through some analysis, a preemptive threshold priority can be chosen to avoid missing deadlines, which is very good. Okay, in conclusion, due to their ease of implementation and administration and greater predictability, deterministic priority policy schedules like RMS are often preferred over dynamic policy schedulers like EDF. But dynamic priority non-preemptive schedulers like EDF achieve significantly higher rates of schedulability with less system overheads. Right? So again, there's greater predictability and it's easier to implement. So RMS quite often is preferred, but not in all cases. However, hybrid approaches like PTS offer a compromise with minor modifications to the kernel and one extra field required to associate the new threshold to a task. Preemption threshold scheduling offers better schedulability overall, also with less risk of urgent tasks being late. Okay, that's it. Hope you enjoyed my presentation. Thank you.